Swayam Prabha. Digital India. Educated India.
Good morning. Let us discuss about boundary layer approximations, what we have been discussing on in the last two classes. In the last class we have derived boundary layer equations, which is the approximations of Navier-Stokes near to a boundary layer formations to a flow past in a flat plate, which is a very simplified conditions. That is what we have discussed. Today we will look at more detailed way how we can get the solutions of boundary layer equations, numerical solutions of boundary layer equations. So, mostly I have been following it the book of Shimala book. So, more detailed derivations you can look at Shimala book, and as I said it earlier, we are talking about the introductions of boundary layer approximations, because we are not going details in these undergraduate course levels. But if you are really interested about boundary layers, there are very good books are available where you can look at the concept of boundary layers. Okay, that is what is I think two professors, okay, Brendel's and his PhD students, okay, Paul Richards and Blesses, they worked hard early 90s to look for solutions for the boundary layer approximations. That is their contributions. Today we will talk about the laminar boundary layers, laminar boundary layers solutions. Then we will talk about a concept of displacement thickness, momentum thickness, and introductions at the flat plate boundary conditions for the turbulent flat plate boundary layers. So, this is what the contributions from Brendel as well as the Blasius. Okay. So, those they have contributed early 1900s where that time there was no computers what we have today. So, how they try to solve this the boundary layer problems to estimate the velocity distributions and the boundary layer thickness. Looking that, let us go for the BC concept what we are talking about. We are talking about laminar boundary layers equations. Okay. So, as if remember it, the boundary layer equations, what we derive it first is the mass conservation equations, which is very simple, as again I am repeating it, for two dimensional incompressible flow, velocity divergence which is equal to del u by del x del v by del y. That is what you just simply remember this part, which is very easy to understand. Remember it, the boundary layer mass conservation equations. So, if I look it as we derive it, the linear momentum equations, linear momentum equations and Bernoulli's equations, both we combine it to get it the boundary layer equations in this form, the basically x direction equations for steady incompressible flow. That is what is coming out to be, as you know it, del u by del u x v del u by del y is equal to, we have u du by dx, this is the free stream velocity, plus you have mu del square y square. Okay. So, that is the equations of boundary layer equations. So, this is the equations which is a parabolic form, okay. Parabolic equations as compared to the Navier-Stokes equations. Solving these two equations are easy because you know it, from these two equations we can get a solutions of u and v, and from that solutions we can get it what will be the boundary layer thickness, what will be the wall shear stress, what will be the screen frictions or drag coefficients. That is what our idea, and what is the thickness of the boundary layers. So, if you look at that, this is a parabolic equations which simplified us, just trying to sketch that part. Okay. So, that means if I have a wall surface like this and you have a formations of boundary layers, that is what is sigma x. Okay. So, that means if I take a control volumes, I know these boundary conditions at the wall is the u, v both are the 0, that is the non-slip boundary conditions. And at this point, at the inlet point, okay, at the section 1 1, I know this the velocity distributions. Okay. That is what we know, the velocity distributions. Also we know how the stream velocity is varying it, u x, also we know it. So, these boundary condition need to be the upstream boundary condition need to apply it. So, by solving these equations today is very easy, because you have a very high computing techniques systems with us, and there are lot of numerical techniques are developed it to approximate even if Navier-Stokes equations. So, if you look at the boundary layers equations are not that difficult to solve today as compared to 120 years back. So, if you look at these are the boundary conditions, and that is the solve we can do it with a time matching scheme. So, more details I am not going it, I am just encouraging you to follow computational fluid dynamics techniques, then you can understand it, how easily we can solve these two equations to get how the boundary layer thickness are there, how the velocity distributions are going on. So, you can get it, and also the pressure distributions and wall shear stress and screen frictions. That is today is possible, because solving the parabolic equations is not difficult with a numerical techniques what is available to us. Now, as the syllabus part, so let us go for a solutions, numerical solutions of the laminar boundary layers. Okay. So, basically we are talking about laminar boundary layers. So, to getting these solutions we are just looking at some simplifications as we did it for earlier case, that we are looking at the uniform speed flow v is going, that is what is the free stream velocity, and if you look at the sketch the same, and very thin plates. Okay, this is thin plate. Okay. Thin plate, because this is to be simplify the conditions that we can get a solutions for this, and basically we are looking at what could be the boundary layer thickness if the free stream velocity is u, okay, and considering it that the boundary layers whatever is here, it remains as a laminar boundary layers. That means, it is a lesser than the critical Reynolds numbers, which earlier I said it should be less than 1 lakh 10 to the power 5. Okay. So, if this is the conditions, we consider the basic properties like density, the dynamic viscosities and the kinematic viscosities are fairly constants for these regions. If I do that with these approximations, okay, that is what we are not going details, but that is the very basic concept is here. That is what is called, if you consider the outer regions, that is what is make it like you have a boundary layer formations, this is the y directions and you have x. So, basically you are considering it's the outsider regions, the velocity of u what is varying it, v is a constant, okay, is a constant. That means, this is the cases what we are looking at. If you look at the conditions what we are looking at, very simplified cases like we have a very thin plates and the boundary layer formations are happening it, and we also consider is laminar boundary layers. For that, if you look at this free streams velocities about just outers of these boundary layers, we can consider this varying with the x, but with a simplify it's that 0 pressure gradient conditions, that is means we are not considering the pressure gradient is a major part for boundary layer formations, then the u x will be the v which will be the constant. If that is the conditions, the same x momentum equations you can now the simplified it. X momentum equations we can simplify it as these u x components become constants. That is what is the graphically representing it. Case of u x equal to the v, that is what is uniform velocity with the boundary layers, how we are considering this is the constants values just out of the boundary layers. Now, as we have a zero pressure gradient concept as a simplifications we have done it. So, that way the basically the x momentum equations is further simplified it as a convective terms okay, is equal to kinematic viscosities del square u by del y square. So, this is further simplified with continuity equations is del u by del x, del v by del y. So, these the equations need to be solved. As I told earlier that for a simplified geometry like this is the our domain, in this domain we need to solve these two equations to know within the boundary layers how the velocity distributions are there, how skin frictions are there. So, to solve this we have a two boundary conditions, as I said it, along these layers we have the boundary conditions u and v is equal to 0, and this is the velocity distributions we know it, and when y equal tends to the infinity and v equal to 0 or u equal to y for all the y x equal to 0. So, that is the regions where is the irrotationality is there. The Blasius as I mentioned it earlier in 1908, which was a PhD student of Prendel's, who is very well known in tolerance studies. Okay. He introduced a similarity variables. I am not going more details to solve these equations with these boundary conditions, that is a non-dimensional independent variables in terms of free stream velocity and v and x, and the y, the directions in the y directions. So, that is the reasons he tried to get it what could be the functions, okay, using the similarity variables. Those are the concept earlier used when we did not have the computers to do numerical analysis. The Prandtl used to do hand calculations based on Runge-Kutta methods, which is today's, you know it, many of numerical techniques is a very well known techniques. So, but he did it a hand calculations to get these solutions, and then he got these equation solvers as if you look it after doing hand calculations and all, he get it that eta value is equal to 4.91, and that is what if he can rearrange it, he will get it sigma the boundary layer thickness by x is equal to 4.91 square root of Reynolds numbers x. So, this is what the boundary layer thickness numerically obtained by Blesses in 1908. Okay. So, and sometimes instead of looking 4.91, people also approximate as sigma by x is equal to approximate is 5 by square root of Reynolds number. Okay. So, we know this what is the thickness of boundary layers, which is for laminar boundary layers. Okay. The same way also he estimated what will be the wall stress. Okay. That is what you know it, that what we can get it if you know this velocity gradient mu times at y equal to 0. So, once you know this u variabilities, so you can differentiate it and mu times find out the slopes at the thin plates. Okay. So, we can get it what will be the shear stress. Okay. So, that is what we will get it, the shear stress value is like this. Okay. And if you divide by the rho u square, then we get local frictions coefficients. Okay. So, local frictions coefficient, I am writing once again half of rho u square, capital U squares, which is coming out to 0.664 of Reynolds numbers. Okay. So, this is what as name it is a skin friction factors or called a Lukan frictions coefficients. That is what is because of this boundary layer force, that how much of force acting on this plate, that is interesting to know it, drag force and the lift force. So, that is what from this boundary layer thickness, for then we can get it what will be the wall shear stress and what will be the screen friction coefficients or the local friction coefficients for the boundary laminar boundary flat plate boundary layers. Okay. Still we are talking about the laminar flat plate boundary. So, that is what you can have a understanding. Now, if you look at more details, if I looking it from the edge of a plate as I go, and if I sketch the boundary velocity distributions, this is what the boundary layers. Okay, this is what the boundary layers. If I sketch the velocity distributions, you can see it like this. The tangent and this velocity distribution at the y, which is representing us mu times is representing us the wall shear stress. So, you can see that the wall shear stress will be more at the front end, but as going back the wall shear stress will be the less. That is the understanding should be there. So, as the boundary layer formations happening it very initial phases, you will have a more wall stresses as go to the downstreams. So, as you go to downstreams, your shear stress decreases, shear stress decreases. So, as shear stress decreases, so you have a more front, you will have a shear stresses. That is the reasons. If you look at the aircrafts wings, we try to design with such a way that it can take it more loads, okay, at the boundary layers parts. Okay. That is the reasons if you look at our forefathers used to sharpening the arrows. Okay. So, that sharpening of arrows, the basically you can understand it how the boundary layer formations happens it, and what could be the strongest materials what we need it at the top of the arrows. Okay, that is the necessary to sustain the boundary layers formations, but the same concept is there. You can understand it that at the front end we will have a higher shear stress, and as you go to downstreams your shear stress decreasing patterns are there, and that is the reasons your the materials what we use it at the front end of a wing, aeroplane wings or aero or missile structures are the more strength, needs a more strength as compared to the downstream part. That is the you can correlate it with the field conditions. Okay. So, basically if you look at the understanding of boundary layers, talk about how the variations of wall shear stress or screen factors. Now, if you look at then another concept what we look at called a displacement thickness. The basically as we know it, the boundary layer thickness developments happens it. Okay. The regions which is closer to that boundary layer formations are happening it. So, the basic idea is comes it as the boundary layer thickness happens it, and if I take a just a pre-out streamlines, okay, just of a pre-streamlines, okay, which I can consider this the streamlines without boundary layer formations. Okay. That is the without the boundary layer formations, the streamline could go on like this as one conditions. Without boundary layer formations, or we are saying that there is no existence of this flat plate. Okay. So, the streamlines which is uniform streamlines what is coming it, that can go as just a parallel to this. Okay. That is why is a uniform stream flow, uniform stream flow is happening it. Now, because of the boundary layer formations are there, the streamlines will not go straight parallel to that, that what will be deflected, that what will be deflected. So, you can understand it because whatever the mass flow is going through these two streamline, that should pass through it, because the velocity at this point the u is lesser than the capital the free stream velocity, free stream velocity. So, considering that, that means the distance that a streamline just outside of the boundary layer is deflected away from the wall due to effect of the boundary layers. That is what I was explaining it. Because of the formations of boundary layers, what is the effect is happening, the free stream which is just the outside of the boundary layers, how much deflections will happen it, how much deflected from that. That deflected part is known as displacement thickness. That is what deflected part of this streamline distance, that is what we will tell the displacement thickness. So, if you look at this is what displacement thickness. So, the basically is the mass conservation equations concept, that we are talking about the mass what will be gaining because of deflecting of these streamlines will be delta star is a displacement thickness into the u, that is what will be 0 to y, or we can put the infinities. Okay. So, mathematically to put it the infinity, some of the books to say it that we do not know this where it is. Okay. That is the reasons we put it 0 to u. This is what the deficit of the mass into dy. Okay. So, I have not multiplied the rho, I have not multiplied the unit depth. Okay. That is not necessarily. So, that way this is what the mass conservations mass component which is pass through because of the deflected of this streamline. This is what the mass deficit it happens within the boundary layers, because the velocity of boundary layers are lesser than the u value. That is how much of mass deficit is happening it. So, if you just rearrange this time, you will get this part 0 to infinity, okay, because we are technically considering it, we do not know where the boundary layer ends it. So, you can integrate it, but no meaning. After this will be the 0 that value. So, we will get 1 minus u by dy. So, if you know the velocity distributions, you can just integrate it, and because this is the free stream velocity, you know it, just integrate it from this point y equal to 0 to infinity. Okay. So, then you will get the displacement thickness. There is a reductions of velocity field near the boundary layer. Because of that, the mass conservation properties to be hold gooded. So, the streamline, which is the outer streamlines, will be deflected, and that deflected part we call the displacement thickness. With simple mass conservation equations, we can get it what will be the relationship. So, if I know the u value, then we can always compute it what will be the thickness of displacement thickness. So, that means we are getting another thickness which is displacement thickness, giving a star here, okay, which is a function of, again just trying to write it to you to again the same functions, but earlier it was 5, it is just close to 1/3 of by the Reynolds numbers at the x. The same way we can get it what will be the as we know this velocity distribution. So, we can get it just doing these integrations, we can get it this value. The equation format will be the same, the trend will be the same. Okay. So, this is what the thickness of the displacement thickness. Now, if you look at what actually helps this displacement thickness is to know it, we are creating a, if I try to understand it, that means we have an actual wall, okay, that is the reasons we put it, this is actual wall, but the displacement thickness gives is as a apparent walls. Okay. So, where we can apply the flow is rotationals and we can apply these Euler equations. So, this is what the velocity distributions very close to the slide with deflection. So, this is what a imaginary apparent wall concept is comes it as equivalent thickness. We have to add it to solve these Euler equations in irrotational zones. So, the displacement thickness help us to create a apparent layers, okay, apparent wall. So, over that we can solve it as a the irrotational zone. So, we can use the Euler equations to solve it. The same way if you look at two-dimensional flow which is happening between maybe the pipe flow or maybe between two plates. So, you can see that this is the formations of boundary layers, okay, and these are the velocity distributions. We can have this velocity distribution, and in a core regions you can have the constants values like this. So, as you go it, so this core flow regions reduce and further we develop a fully developed velocity distributions profiles starting from entry which is uniform stream bill. That is what as equivalent when you put it, this is actual velocity distributions and the core regions. Instead of this, we introduce the displacement thickness. Okay. So, this is the displacement thickness part, and these displacement thickness outsiders, this is Euler equations. So, we can assume it more or less the uniform velocity distributions within this. Okay. So, we consider the afferent layers, thickness layers as the regions beyond that it is representing for us the Euler equation solvers. So, this is what help us for real conditions to coming to a afferent wall concept. Between these afferent walls we can consider is a flow is as equivalent to irrotational flow, and we can use simple stream functions and velocity potential functions and the Bernoulli's equations to solve the Euler equations to get it the flow patterns, the velocity distribution pattern. So, the displacement thickness gives us to develop the apparent wall concept, where we can use Euler equations to derive that. Let us come with a very simple problems which is there in Sinjan Simbala book. There is a low speed wind tunnels being designed for calibrating the hot wires. Okay. Air is at 19 degrees. So, this is the air flow systems. The test section of this wind tunnel is 30 centimeter diameters. Okay, that is what is. Okay, this is 30 centimeters, the test sections, and 30 centimeters in the length. So, the length is given to us. The flow through this test section must be uniform, because that means we have to look at what is the laminar boundary layer thickness. It should not have the turbulent boundary layers, because then we cannot make a test section for. So, we will be try to make it the test section such a way that laminar boundary conditions prevails, as well as you have to look at what is the amount of thickness is coming it, which is will be appropriate for a displacement thickness and also boundary layer thickness. With a speed tunnel speed 1828 meter per hour and the air speed is 4 meter per seconds. So, we need to know it that how much will be central line air speed accelerated by the end of the test sections. Okay. That is the things where I am not going all the steps by. So, we have to flow is steady, incompressible, wall is smooth and disturbance vibrations are kept minimum. You just find out the kinematic viscosity of air at the from any tables is given in the book of any fluid mechanics books and all. So, estimate what will be the Reynolds number end of this test, because test section is 30 centimeters. Okay. So, is a circular test sections. So, the basically at the initially you will have this 30 centimeter, but at the end you will have a boundary layer formations. Will you have boundary layer formations at the leading edge? There will no boundary layer formations, but at the end we have the boundary layer formations. What is that thickness? What is the Reynolds numbers at these points? That is what you can compute it. The Reynolds numbers coming about 7.96 10 to the power 4, which is lesser than 10 to the power 5. So, the flow is laminars, that is critical numbers, sometimes 5 to 10, 5 million, 5 lakhs we consider it, but it is okay. So, we can consider is a, as you consider is a laminar flow happens it. So, now you are computing the displacement thickness, just substituting the displacement equations, we can get it the displacement is coming in order of close to the 2 mm. Just you look it, I always you demonstrated think it which is not visible. So, okay. Mostly we ignore that part, but that is what is majorly controls the boundary layers, how the drag force or lift force are happening it, and how the shear stress distributions are happening it. But thickness of as you demonstrated by these examples, thickness in the order of millimeters, the diameter is in terms of centimeters. Okay. So, that way you can understand it how difficult it was to measure the boundary layers in almost 120 years back. Okay. So, now we have a lot of advanced fluid mechanics equipments, we have high computational facilities. So, we can conduct very detailed experiments, but 120 years back understanding the boundary layer concept, derive the solutions of boundary layer equations by hand written hand calculations, that is what was quite appreciable. Now, we come to the momentum thickness, which is not big, the concept which is already we talk about shear stress, displacement thickness, also the wall shear stress. Same way it's come the momentum thickness. That means, as you know it, we apply the control volume concept. So, we will apply the control volume concept to know it what will be the drag force is happening it. So, what will be the drag force is happening it on this plate. So, that means, let me I sketch it the problems. If you look at that same things I am defining to here, this is boundary layer thickness. I am taking this is my control volume. This is my control volume. Okay, that is what very beginning I said it. This is what my control volume. So, there will be a force acting on this plate for drag force in the x directions, drag force in x directions f dx, that is what will be act on this, and from this I know uniform stream flow. At these points I know it, as I was telling it, that I have the velocity distributions. Okay. I have velocity distributions, then I have the uniform velocity distributions outer of these boundary layers. That is what is representing here. Mass deficit, and this is the delta displacement thickness is showing it how much extra mass, that these two be equal each others, okay, above these free streams, okay, above these free streams. So, the mass flow deficit due to the boundary layers, and that is what is mass, that net mass is equate. That is what I used to derive for the displacement thickness. Same concept is coming it, but here we will use it as we have done for integral approach. So, we will equate the momentum flux, influx and outflux, and then we will try to find out what will be the drag force. So, this is a simple case representation. If you take a control volumes and you try to equate the momentum flux way in and out, and try to find out what will be the drag force acting on this plate. Okay. That is what looking from this, as I earlier I derive it, the same way I can get it the mass flux and the relationship with the displacement thickness. That is what it already I derive it. So, you can see it. Now, we are applying it as for these control volumes, we are applying it, the sum of the force acting is equal to the net momentum outflow flux from these cross sections. It is a two dimensional cross section. So, we can define it what will be the cross sections momentum flux is going out. So, this is in, this is out. So, if you look at that part and just rearranging the drag force components and x that, then you will getting the drag force. Okay. Momentum thickness is nothing else, it is talking about only the skin friction factors. Okay. It is just introduced as a momentum thickness as equivalent to moment change because of these boundary layers. So, it is defined as viscous drag force on the plate per unit width. Okay. That is what is mentioned it, okay, which is equal to rho u square theta. Okay. That is as a equivalent representations. That is what if you look at for drag force, viscous drag force, which f dx by per unit width w, and that is what is the momentum flux net, what you, and you are equating by rho u square. Okay. That is the momentum thickness, and you can have a simple calculations, then you can get it very simple way. The you can remember it 0 to y, okay, is equal to small u, and by capital U this is a free stream velocity. So, this is momentum. So, you can see this the multiplications with a u. Okay. That is what is the momentum thickness, and many of the times we y we represent as infinities and mathematical point of view, as I told it earlier. So, we define it as the momentum thickness. So, we can get it what will be the momentum thickness, which is a as equivalent to the skin friction factors. That is what you can understand it, because we derived it considering a control volume, or you can derive from the velocity distribution, both are the same. So, but we have the different naming, the momentum thickness or skin factors, okay, friction factors, okay, but the both are the same. So, that is not a way, as theta is the same as the delta delta, but with a different constants values, okay, if you can say that 0.66 pound by r, and which is a 13% at the locations x. So, mostly this type of concepts comes in a GATE or engineering service, but you try to understand it as equivalent of thickness we are representing for displacement thickness as well as the momentum flux thickness, because the change of the flux, what is the net force acting as a skin friction factors on a flat plate due to the formations of boundary layers. That is the points we are talking about. Now, we are not going to more details. When you go for the turbulent boundary layers, just conceptually I will discuss with you. It's a very complex equations it comes out to be. So, the turbulent boundary layers, basically we do not get it hand calculations based, even if numerical techniques to solve these problems, because as I introduced very simple way to the turbulent boundaries, a chaos flow with a fluctuating part, the time average components are there. So, instead of that, the people just try to look at the standard formulas, okay, which can enough to give the velocity distributions in the boundary layer regions, the turbulent boundary. So, one of the very basic equation is that we call these time average components. Okay, I will show it basically empirical natures. That means mostly we are trying to get it from experiments and try to fit the equations and find out the equations. Okay, which is more famous equation for the time average velocity profile is 1/7 power law. Okay, that means u the velocity by the free stream velocity. Again, I am just sketching it. Okay, you have the velocity distributions for the turbulent flow, and you are just looking at what is this distributions, okay, which follows, this is a y directions, which follows approximately, okay, again approximately 1/7 power law, okay, just non-dimensionally it just look at these ones. Okay, this is the empirical equations, and we can try to understand it, that when y will be greater than boundary layer thickness, then the velocity ratio becomes, this non-dimensional way, the velocity distributions is defined by the 1/7 power law. Okay, so I will show it that. So, the basically we are trying to look at the turbulent layers, and you try, as I introduced earlier, it will have a large eddy formations, and there is a lot of mixings happens it, and really very interesting subject, I can say it. If you are really interested to learn more turbulent flows, which last almost 20 to 30 years, we spent a lot of resources by many scientists to solve these turbulent flows. So, you can really get knowledge on the turbulent flow, but in this undergraduate course we are not going details. So, basically one very simple empirical equations obtained from the experimental data is called 1/7 power law. The same way the equations what give is different formats, we will go for next, but if you look at that, when you have the shear stress, okay, to estimating the wall shear stress, okay, which corresponding to the high screen friction along the surface, okay, compared to the laminar boundary bed, because if you draw the velocity distributions, so you will have the high wall stress in turbulent zone as compared to the laminar flow. So, that was high shear stress development will happen it. This is showing it the comparisons tables, okay, only for the smooth plate boundary layer thickness, displacement thickness, the momentum thickness, and local friction coefficients, which we have derived for laminar flow. Okay. So, as I said it, momentum thickness and local skin friction coefficient both are the same. So, okay, that is only we define in different way. If you look at the turbulent flow, you can see that how the thickness will be quite less as compared to the boundary layer laminar flow, but if you look at the value of local skin factors or the momentum thickness is much larger. Okay, this is what you can understand from this. Okay, it will be much larger. That is the same way. This is the 1/7 power law, because but this law does not hold good for all the cases. They use combined with the empirical for the smooth pipes. Again they changed the relationship between boundary layer thickness, displacement thickness, momentum thickness, and local skin friction coefficients. If you look at that in the turbulence things, a lot of studies were conducted to get it the best approximations of boundary layer thickness and these properties in turbulent zones. So, these are all can be said is a approximations. So, similar way there is a log law, okay, which establishes the relationship non-dimensional way, a relationship between here if you look at the U star subscript star is a friction velocity, okay, it is not a velocity, it is as equivalent to the dimension of the velocity, but is representing about the tau is the bed shear stress, the wall shear stress by the rho. It is a dimensionally it is looking the velocity, it is but due to the frictions. So, that is the reasons with a friction velocity and that is what the velocity distributions, not the 1/7 power laws, but log law concept has come it with having the A, B are two constants, which is you can varies from 0.4 to 0.41 and B varies this. So, we get it the log distributions of velocity in boundary layer regions will give us the value of y u star by kinematic viscosity plus B, and here K and B are the constants. I am not going more detailed about what is the constant's name and all, but you can see that the log law can be used. This is the instantaneous velocity distributions. The time average velocities will come like this. So, we can establish the relationship between velocity distributions with the tau naught, the bed shear stress, okay, bed shear stress, and as a logarithmic functions, non-dimensional logarithmic functions, we can use it to have the these relationships. Okay. So, same way it has been tried by many. I am not going details about splending clause, Wahlbeck clause. Okay. Those are interest on the turbulent flows. I think I can just advise you to take it the advanced level of fluid mechanics book, read the advanced or the courses which really give you interesting fact how these equations are derived, how we have been trying it to make it better way to present this turbulence flow velocity field, okay, which is very chaotic or complex. That is what we try to do it with empiricalisms, with some concept like from experimental data. So, the equations are the different and they have a really utility for different case of this. With this let me conclude boundary layers approximations. As I said it very beginning, we are talking about introductory levels, and these are the three equations as we talk about boundary layer equations, displacement and momentum equations, and that is what we have derived it, and many of GATE or engineering service things are comes under these displacement thickness, momentum thickness, and some part of how to estimate the boundary layer thickness, that things are there. With this, let me I thank my student groups who really have put a lot of efforts to prepare this presentation. Thank you. Thank you.